Okay, I guess we'll get started. So I wanted to say a few general things, and then we can go over some of the review problems I put on CampusWire from last year. And then we can talk about any questions, or we can actually talk about any questions as we go along. But as usual, we got to talk about the fact that as this is a Columbia thing, and Columbia is seeking to get more grants to develop STAN, and using STAN outside of Columbia, that creates the appearance of a conflict of interest, but you should know all that by now. So the exam is going to be a week from now, from 4:10 to 7, unless you have like 2 other exams that day or something like that. We can probably come up with alternate arrangements. The exam is not going to be in the math building. It'll be in IAB up on the 4th floor. So you should bring your laptops, bring your power codes. You can use all the notes. We don't have really any books, but you can refer to any of the stuff on the internet. Just make sure that you have all the R packages that we've used this semester and that they're working. So sometimes people, like, particularly with Macs, have been updating the operating system, and then some stuff doesn't work. So just make sure everything is working before you come. All right. Smaller. Slightly smaller. Much smaller. Okay. So a lot of what we've been talking about over the course of the semester has revolved around this idea of using or referring to a generative model. And if you don't have a generative model, meaning a model that you can simulate from, you can't really update your beliefs using Bayes' rule or do a lot of the other things that we've done this semester. And so this is a step that people often try to skip and shortcut through. But I think it's worthwhile to plan out the analysis that you're going to do, and to start with a more simple one before you start making things more complicated, or moving something from exogenous to endogenous or something. So the exogenous, let's start with the endogenous known. That is the outcome or the outcome variables that you intend to model. One of the real advantages of the Bayesian approach is that you can have multiple outcome variables or multiple endogenous known variables simultaneously and incorporate all that information. So we saw it with bowling, and we saw it with instrumental variables, and we saw it with the mixing models framework in the Humphreys and Jacobs paper. Just having multiple endogenous knowns that you're trying to model as a function of the exogenous knowns. So those are going to be, the sizes of various data structures, what the predictions are, and then any stuff you need to evaluate your priors on the exogenous unknowns, or the parameters. So the parameters, everything to the left of the vertical bar in Bayes' rule. But parameters is maybe overly specific. That could also include true values of missing data. So data, if you'd observed it, it would have been known, but if you don't, then it's unknown, or true values of data that you might not have measured correctly. Other things that are pretty common just sort of fall in the unknowable box. And then the last one, the endogenous unknowables. These are things that we don't know because we don't know the values of the exogenous unknowns. But if we knew the values of the exogenous knowns, or we had proposals for the exogenous unknowns, or yeah, go up. All right, massive influx. We have not gotten very far. So I just said this information and like that. Anyway, so and then I was talking about in the last box here, endogenous unknowables that we would know them if we knew the exogenous unknowns. So these are usually known functions of the exogenous unknowns. But if we had proposals for those, if we had a distribution of those, we could evaluate. So that would be not only intermediate quantities that you need to evaluate, like the log likelihood, in which case they're just kind of a placeholder, some placeholder function of the exogenous unknowables, but even more fundamentally, predictions of new data, evaluating your utility function, if the parameters were this or that, those all fall in the category of endogenous and unknowable. So if we were going to do this in a STAN program that you write yourself, then the data and the transform data blocks would contain the known things. Definitely the exogenous knowns should go into the data block. We can use the transform data block to draw endogenous knowns if we're doing like a SBC thing. Otherwise, if we're just conditioning on data that we've collected, then the data block would also contain the endogenous known values. And then the parameters, whether we're talking about sort of pure parameters or missing data or true data that has been mismeasured somehow, that would contain the exogenous unknowables that we want the posterior distribution of. And then the model block is obviously going to build up this expression for the numerator of Bayes' rule using log units. But we can put endogenous unknowns in different places depending on some things. So the transform parameters block, if you define anything there, it can contain endogenous unknowns, functions of the exogenous unknowns that are one of interest to you. So you want to look at what their posterior distribution or implied posterior distribution is, given the posterior distribution of the exogenous unknowns. But there also should be needed to evaluate the log likelihood in the model block. If they're not of interest, then that's fine. You could just define them in the model block and they wouldn't be saved in the output. It got cut off on this, but and then the generated quantities block can be used to evaluate endogenous unknowns that are of interest but not needed in order to evaluate the numerator of Bayes' rule in the model block. So those, Stan doesn't have to do derivatives and stuff with respect to them. So that can all be put in the generated quantities block to save those sorts of things. Or you can just get the posterior distribution or the draws from the posterior distribution and then do as matrix, as data frame, extract, get the 4,000 or however many draws of all the exogenous unknowables that you need. And then in R, just evaluate those functions yourself. So you don't necessarily have to do it in STAN code, although that is often the most convenient. And so that is really an important step for any Bayesian analysis. Presumably you're going to be using STAN. There's lots of reasons why that's true, but this is sort of more at the level of concepts than, or a prerequisite before you go about trying to draw from the posterior distribution that you've defined. And this would be more or less the same even if you were doing a frequentist analysis without all the prior stuff. But you could use Stan to evaluate the distribution of a point estimator or things like that. So this is one of those things that we were talking about earlier in the semester, and it seemed that a number of people didn't really appreciate the importance of thinking through these steps until later on, particularly when we got to situations in which we had, a predictor of one thing, but it's actually an endogenous known because it, is sort of an intermediate outcome. It serves as a predictor for something else. So just because you classify something as a predictor doesn't necessarily mean it's an exogenous known predictor. I think this is one of the distinctions that the supervised learning approach to quantitative methods really misses. So if you set something up and you're predicting, like just doing like least squares or lasso or something, and some of your predictors are in fact endogenous, that's not particularly good in any sense. But one of the senses in which you could, definitely be in trouble is, okay, we're going to predict future data, but you have to wait until the intermediate outcomes become available before you can make that predictions in the future. And by the time you've waited to that point, you probably have the ultimate outcomes anyway. So why are you predicting them? I mean, the real value of doing these predictive exercises to make predictions in the present, in decisions based on those predictions in the present about the future. And if you have to wait for intermediate outcomes to come in, it kind of makes that whole process irrelevant. And so the Bayesian approach can definitely be used for prediction as well. And if you set up a real generative model, you ought to be able to predict the intermediate outcomes in the present that are going to transpire in the future, and then carry through with your utility function and all of that. So questions about generative models. I mean, I know we've talked about that a lot, but for as much stuff as we've covered, the exam is definitely going to be about things that we've touched on a number of times, just maybe in like a bit of a different form or a different way. So this is certainly going to be one of the good ways to organize your thinking about a lot of problems that you will encounter, not just on the exam, but more broadly speaking with research and analysis and quantitative methods in the social sciences and stuff like that. Questions about this? Okay. So another big thing that we talked about probably on the first day, but also a number of times after that, the 4 different sources of uncertainty in analysis. Uncertainty about what are the values of the parameters that we put in our models. Uncertainty about which model or set of models is best. Uncertainty about what to do with the output in order to make a decision or take some sort of action. And uncertainty about whether the software is working as advertised or as intended. And that those 4 things we want to go through from a Bayesian perspective, and also talk about how that contrasts with some other approaches to quantitative methods. And so the essence of the Bayesian approach is for each unknown number or unknown in a model, use a known probability distribution. And that known probability distribution should represent what you believe about the parameter. And so the practice until fairly recently of putting improper priors on parameters is not a particularly effective one, because you can't draw from an improper distribution. It's not an actual probability distribution, it can't possibly represent what you believe because it doesn't integrate to one. And so saying, okay, this thing could be any real number and all real numbers are equally possible is not a coherent set of beliefs. And it makes it, impossible to actually draw from any of these. But as long as you're using well-defined probability distributions, anything you don't know, you can just put in a distribution that represents what you believe about it. And then the addition and the multiplication rules, particularly the multiplication rule, allows us to combine probability distributions, and we can compose a joint probability distribution with, a marginal distribution on one thing and a conditional distribution of something else, given the realization for the first thing, to build up joint distributions over all of the unknowns. And then we can obviously use Bayes' rule to condition on endogenous but known data to then get updated distributions of our beliefs about all of the parameters that we initially specified a prior distribution on. Rarely are we going to be able to have an analytical form of that conditional distribution for all the unknowns given the known data. But that's okay, because having many random draws, as long as those random draws are not too dependent on each other, give us a representation of that probability distribution that is actually a lot more useful than having a PDF or a CDF or something like that for our posterior distribution. Because if we have a bunch of draws, then we can evaluate functions of interest point-wise. And so we can just take the mean of a bunch of points, and that is, an estimator that converges to, the expectation, which is actually an integral that we might not be able to actually evaluate analytically. And so having the ability to produce a whole bunch of draws, and Stan can do that as long as your Bayes rule is differentiable with respect to the parameters, is an important thing. And Stan is really good at going all throughout the parameter space, everywhere where there's non-negligible amount of probability of obtaining a draw. It's going to do that with the appropriate amount of probability if everything goes well. And a lot of times things just do go well, but if they don't, then you'll get warning messages about that. And so in a sense, it's very good that we have Stan. It makes the inference very reliable, or at least noticeable if it's not reliable. But most of the hard work comes before you even sit down to draw from the posterior distribution, in terms of thinking through your models, like we referred to before with the generative model process. And also another reason why it's good to have draws is your intuition often fails you, and it often fails a lot of people when talking about multivariate probability distributions. And so it can cause people to come with a lot of wrong conclusions. And so one way to avoid that is just take the draws and pump all those draws through whatever function is of interest to you, and then look at a margin or whatever it is that you want to do with that. But just allows you to be explicit about what functions and whatnot you're applying, rather than trying to get some sort of intuition about things. So one of the things that turns out to be counterintuitive is correlation matrices. So your intuition is sort of well, as the size of the correlation matrix gets bigger and bigger, there's more and more correlation matrices that I have to worry about. But that's actually not true. As you get more than 6 variables in a correlation matrix, as you start adding more and more variables, the volume of valid correlation matrices actually shrinks. So the dimension of your space that you're getting a correlation matrix on the variables on can expand from 1 to 2 to 10 to 100, etc. But as you get like past 6 or so, they get crammed into a smaller subspace of a larger and larger dimensional space. So like the volume of correlation matrices goes down, it gets more and more concentrated around the identity matrix. So as like the dimension gets bigger and bigger, the draws of the correlation matrix get closer and closer to the identity matrix. But if you just have the draws, you can see that, even though it's not the most apparent thing. Another way in which your intuition can fail you, particularly for like multi-level models, is a mode, even a posterior mode, can be very far away from a posterior mean or posterior median. Particularly the joint mode can basically be like anywhere in the parameter space and have no particular connection to a posterior mean, posterior median. The mode can often be on the edge of the admissible parameter space, even when most of the draws are well interior to the parameter space. So there's a lot of confusing things that go along with probability of random variables in multivariate spaces. But if you have draws, you can just investigate all that. Whereas if you're just trying to do it with Mathematica and stuff, you can sometimes get nowhere and sometimes get a valid answer, but it's not one that shines a whole lot of intuition on the process that you're studying, like being able to evaluate 4,000 draws worth of it. Questions about that? So the second source of uncertainty is uncertainty about which model is best. So one of the things when evaluating a question like this is to say best for what task, by what criterion. But once you've answered that question, we have a lot of options in the Bayesian framework with which we can answer a question like that. So if what you mean by best is, well, what is expected to predict future data best? Well, we have expected log predictive density, which is one of the most core ways of evaluating prediction success. It's not one that you see used in supervised learning very much because they don't talk about density functions explicitly, nor do they have probability weighting with which you could take an expectation over the future data. But with the Bayesian framework, we have that, and that's something that we can estimate from the posterior distribution pretty well, actually, just by calling Lu in the Lu package. There's an assumption there that you could leave out one observation without having a very large effect on the posterior distribution. And if it's not too large, then we can accomplish that pretty well just by reweighting the existing posterior distribution to reflect what if we'd left one out. If it does have too big of an effect, we can't really like bridge that gap with importance sampling, with the number of draws we have. Then it'll tell you, okay, you should re-estimate this thing, actually leaving out observation 4, and then we can get a expected log predictive density from there. So that all works pretty well if your question is which model is expected to predict best future data. We can also learn how to get weights over different models such that the weighted sum of the predictions of various models is expected to have, or is maximized, the collective expected log predictive density. So it's entirely possible that some combination of models that you estimated is expected to predict future data better than any one model, or at least you could check and see if the stacking weights are not just like 1 on one of the models and 0 on everything else. So the Bayesian approach gives us a principled way to combine predictions from different models that don't necessarily have to be nested. We also learned about the projection pursuit approach in the ProjPred package that would allow you to, first get the posterior distribution of a more complicated model, maybe one that has like hundreds or millions of predictors and something like that. And then gives you a principled way. How could I choose a simpler submodel of the bigger complicated model that has almost the same expected log predictive density, but fewer predictors? And that can be important or useful when, for example, it's expensive to collect data on all those predictors. And so you might say, okay, well, can we get away without having to collect data on this, which is expensive, but still get about the same expected log predictive density from a simpler model? But if you really have like more predictors than observations, or just like a lot of predictors generally, and not much theory as to what should be included in a model, you'll often need priors that have more concentration near zero than like the default priors that we usually do in our RStan-ARM and things like that. So if you just have like a couple of or a few like well-chosen predictors, oftentimes you can get away with a normal prior that just sort of reflects your belief about those coefficients. But if you're just sort of throwing a lot of predictors at something, then you very well may want to use a prior that reflects your belief, and this is a belief that a lot of people have, that almost all of these predictors are going to have like pretty much zero effect, but I don't know which ones those are. So want to use a prior like finish horseshoe or product normal. Some of the things that we've talked about have more or a high amount of concentration, high amount of density right at zero, but heavy tails. So allowing for the possibility that a small number of predictors really could have coefficients that are far away from zero, but by and large, trying to shrink small coefficients to be really near zero. And this is actually kind of a better way of doing what the lasso approach does, which can be thought of using double exponential, otherwise known as Laplace priors, on the coefficients, which it's the double exponential distribution isn't really that great as a prior, because it doesn't put enough density at zero and the tails aren't really heavy enough. So it ends up shrinking these non-zero coefficients quite a lot and doesn't really give you the best distribution for expected log predictive density and things like that. So a lot of the ideas from supervised learning, or a lot of the goals, I guess, from supervised learning can carry over to a Bayesian analysis. But one of the things that I think a lot of people on the supervised learning side kind of overlook when we say, oh, like all these penalty functions that supervised learning people are using can be thought of as priors. They often make for pretty weird priors, because in the supervised learning, penalty function context, they're only worried about how that penalty function affects the mode. And, maybe the mode becomes zero or whatever, because all they're going to do is optimize to find the mode, stop, and use those one numbers to make all the predictions. But if you consider this from a Bayesian sense, from a generative model sense, you have to also think about, well, how do those priors affect the tails? Because that's going to have a big influence maybe on the posterior distribution or on functions of the posterior distribution. Whereas from a supervised learning perspective, it really doesn't matter what's going on away from the mode. So that's that. And an not entirely different, but fairly different approach that we talked about briefly is getting posterior probabilities over models. So what's the probability that this model is correct, conditional on the correct model being among the set of models that I estimated, basically applying like the Clogit likelihood function to models. So if you have like a prior over models, which is almost always going to be uniform, like every model has the same chance of being correct a priori. And then you use the denominator of Bayes' rule. For each of those models, you can renormalize it and get posterior probabilities over models using the bridge sampling package. And that works with RStanArm and BRMS. You could get it to work with your own STAN programs, but it's easy to just call it when something is estimated with RStanArm or BRMS. And like we said, well, the real problem, the reason why we have to do simulation in the first place is that we can't write the denominator of Bayes' rule in an analytical form. Well, after we get the draws, it is sort of possible to approximate the denominator of Bayes' rule and thereby get these posterior probabilities over models. But a lot of Bayesians really like this approach, and then a lot of Bayesians really don't, because they're not comfortable with the assumption that, well, one of the models in the set of models that you estimated was correct, or they're uncomfortable with how sensitive the results of this exercise are to choices you made about the prior that affect the prior predictive distribution, but after you condition on the data, that's all sort of like water over the bridge. It's what I used to believe, rather than what I believe going forward. And so this whole idea about posterior probabilities over models basically involves a contest to see which model's prior predictive distribution turned out to be most consistent with the data that you observed, collected, and conditioned on. Whereas some of the things that we talked about before, expected log predictive density is, which model is expected to predict future data the best, which model has the expected to have the best posterior predictive distribution of future data. And so you could see these different approaches as like, at which stage of the analysis are you sort of doing this? Do you care more about which is expected to predict future data best, or which model previously predicted the present data the best? And so those are some of the things to keep in mind when thinking about this debate, which is mostly within the Bayesian camp. There's not really anything you can do from a frequentist perspective or from a supervised learning perspective to say, like, this model has a 0.7 chance of being right. That's just not something that you're going to get from anything other than the Bayesian approach. Questions about this? So the third source of uncertainty is sort of more fundamental uncertainty. What should we do next after we've gotten the results of the analysis? And so back in the 1930s, I think, it was, or maybe 1940 or so, by a guy actually at Columbia, it was proven that every rule for making decisions is one of three things. It's Bayesian, it's the limit of a Bayesian decision rule as like the number of observation goes to infinity or something like that, or it's dominated by a Bayesian rule. And what dominated means is that whatever other thing you're doing, it's no better than some Bayesian rule for any value of the parameters that you don't know in the parameter space. And the Bayesian procedure is better for at least one value of the parameters in the parameter space in terms of like minimizing expected loss. And so that was a very consequential result. And as a result, the person who derived it wasn't even that comfortable with the implications, because he had sort of previously thought of himself as being a very strict frequentist and set out to show that like these Bayesian decision rules were not good, but he ended up actually sort of proving the opposite from what he thought he was going to prove, and that was something that motivated him, at least privately, to say like he was, thereafter thinking about things in Bayesian terms. But in the 1930s or 1940, whenever it was, that would have been like a professionally suicide thing to really say that like I'm Bayesian, given the dominance of Fisher and Neyman Pearson and stuff at the time. So that was a pretty profound theorem that got proven then. And, the Bayesian decision rules are basically those. It says, okay, make the decision, take the action or whatever that is expected to maximize your utility function. And that utility function is going to depend on, the unknown parameters that you just got the posterior distribution of, and, different decisions that you could make. But you can just evaluate the distribution of utility or a bunch of draws from the distribution of utility for different decisions that you might make, and then choose the one that has the highest expectation. That is a very principled way to make decisions that follow from an analysis that's being done. Of course, you have to specify your utility function along with everything else that goes into Bayesian analysis. But once you do, it's a very principled way to make that decision. And we talked about that really, first homework with that poker problem, or alluded to it, I guess, a little bit. Didn't quite get all the way there on like the second problem or the second homework about the equilibrium temperature climate sensitivity thing. So like if you put in some utility function over future temperatures, well, if we heat up the planet 3 degrees, like that's going to have like all these costly consequences. And so that would sort of point you toward making a decision in the present to do more to reduce greenhouse gases and other sorts of things, because the expectation of that process is real bad, considering the heavy tail of uncertainty that we have about temperature of the Earth decades or centuries in the future. That heavy tail really has a big contribution to expectations in the like not auspicious direction if we don't do anything about it. So there is a sort of frequentist version of decision making that is kind of weird, but usually what it results in is like, here is the decision that would maximize your utility in the worst case scenario. Like everything frequentist, it's like averaging over different data sets that could be drawn from the population. But it sort of says, okay, what is the minimax approach here? What gives you the most utility in the worst case scenario? And so in every other scenario, it's going to be a little bit better than that, is sort of maximizing this lower bound to what utility is. And like there's tons of papers that derive these minimax estimators, but it's hard to find a situation in the real world in which like that is your approach. It's no way to run a business or to conduct policy just worrying about what is the worst case scenario and making that as good as possible. I mean, it's still going to be bad, but mitigating that. Anyway, even that approach, the minimax thing, can be shown to be equivalent to a Bayesian one with very, very weird priors on the parameters. And so the Bayesian approach actually subsumes that one as well. But one of the things that I think is overlooked because supervised learning sorts of approaches are used so much in businesses, in business analytics and stuff like that, is that they don't really have a principled way of making decisions from a supervised learning analysis. It's just like we predicted, here's the one that gave us the best number of correct classifications or whatever. And now what do we do with it? It doesn't really get you all the way there toward making a decision, because decisions have costs and like all that has to be considered, and the function that you're using to say like this model is better than the other one because it has like a higher amount of specificity or something like that has really no connection to like the profit of the business, or no obvious connection, no explicit connection. But you can't, because you don't have a probability framework underlying it. You can't really go from like this model has the greatest number of expected correct, or greatest number of correct classifications and the held out data to, if we were to go like follow the implications of that model, how much profit would we be making? Is that more than if we did something else? It's not going to tell you. And it's certainly not going to tell you anything about expected profit, expected utility, because it doesn't have the probability weighting that you have with the Bayesian approach. And so, supervised learning is definitely funded a lot by businesses that sort of think of themselves as being like pragmatic and not overly concerned with academic debates and stuff like that, and using these sorts of techniques, but then they just sort of wing it when they get to, okay, now what do we do with the model? When there's actually like a very principled set of steps that you could follow if you took the time to actually get the Bayesian version of the models that you're trying to estimate. And that's, I think, one of the virtues of learning the Bayesian approach, is that it can be applied to everything. And so I think there's a lot of push out there for, if you don't care about the parameters, you just care about the predictions, then like do random forests. And if you have an experiment, do design-based inference. And if you have a survey, do frequentist inference and these sorts of things. Whereas the Bayesian approach actually would work in all of those situations and pretty much any other situation we can think of. So it's a very general approach, and one that if you learn how to do it well, it's quite likely to be applicable no matter what it is you're asked to do or choose to do in the future. Questions about that? All right, and then uncertainty as to whether the software works. That's hard to integrate into the previous. So you might want to, in principle, like hedge your optimal decision depending on the probability that the software is like malfunctioning or something like that. But we do as much as we can. And I think we do much more than what a lot of other people are doing, the right software to make Stan work well, but also tell you when it's not working. So all those warning messages that you sometimes get when things don't go well, about like this didn't converge, or the effective sample size is way too low, divergent transitions, low Bayesian fraction of missing information. If you didn't see those messages, that's mostly because in the examples we did, even some of the more complicated examples we did, things went well. But as you start writing your own Stan programs, you'll often get these messages when you're starting out, because you make mistakes, or your program is like valid, but it's not optimized enough. It has numerical inaccuracies in the gradients, things like that. And then, the first like 20 models you try to do yourself, all you're doing is getting these warning messages. But that's good because it tells you, you wouldn't want to trust these results unless you can, improve things to make those go away. And so, particularly with divergent transitions, one of the first things you want to do is increase the adapt delta tuning parameter. That will tend to make Stan take smaller steps and not miss parts of the parameter space that have positive probability under the posterior distribution. But, that's going to tend to make Stan have to take more steps, more function evaluation. It's going to go slower. But there's way too much emphasis out there, particularly for applications in the social sciences, about how quickly software runs. No one's cost function is really like particularly sensitive to those sorts of things, particularly relative cost things. So the fact that Stan takes like 1 billion times longer than something else is not really relevant as long as it runs like, fast enough. So for most purposes in the social sciences, your like cost function is, it takes too long or it's fine, no matter how long it takes. But most of the social science is sort of fine, even if you have to run something for like an hour or a day or a week or whatever. There's stuff in like finance where it's important to have an answer in like a few milliseconds. But those aren't using Bayesian methods, not that high frequency stuff. They do use Bayesian methods for some of the more like longer term investing strategies. And those tend to work really well because it's a very Bayesian approach. Like, how would we maximize expected return of investments subject to some constraint that we don't want to exceed some threshold for risk? That works well. But for high frequency stuff, there's no way you can get a posterior distribution fast enough to be able to do something like that. Another tool that we learned about in the last couple of weeks, simulation-based calibration. So draw from your priors, draw from the prior predictive distribution, condition on those realizations from the prior predictive distribution to get a posterior distribution, and that posterior distribution should not be systematically different from the prior distribution you used to draw the parameters from. And if you do that over and over, you should see that, in fact, if everything is working well, there's not a systematic difference between posterior and prior when conditioning on data that is generated according to the generative model that underlies, your Stan program. And so that can be used to establish, for the N that you have, for the priors that you have, for the exogenous knowns that you have, Stan is or is not going to work well across endogenous distributions of endogenous knowns that you could obtain under your model. You may have to like increase the adapt delta or something like that, but you can ascertain to a high degree of certainty that Stan is going to work well in this particular situation. And then when you get actual data on the outcomes, can be confident it should work well. And then, if you go through the SBC thing and everything is looking good, and then you get some data and you plug it in for real, commenting out all the SBC stuff and putting the endogenous known up into the data block instead of the transform data block where you draw it, and you get a lot of warnings, things aren't going well. Well, that is a very good indication that the outcome data that you collected wasn't actually generated by the generative model that you proposed. Because when the data was actually coming from the generative model, you established that things were working good to a high probability or whatever. And so if things don't work good, that's another indication that helps you know that maybe you need to rethink your model. Another thing that, Bayesians find like very irritating when people say, well, Bayesian or MCMC or STAN or whatever, it takes way too long. Paul Bergner wrote like the BRMS package, which is awesome. Like every time he does a presentation, he has this story about like a student who came into his office hours and was like, yeah, I like the Bayesian approach, but it's taking me too long. And Paul said, well, like, how long is it taking you? And the person said, well, a minute. And it was just like, do you realize the ambition of what the Bayesian approach is trying to do, to draw from the posterior distribution, like the whole parameter space in accordance to, every draw having the right amount of probability as opposed to just getting one number and stop. And you're worrying that it takes a minute to get the results back. Like you just have a way distorted view of your own value of time, particularly because like, you can just start it and then like go to the movies or make a sandwich or something. And then like come back when it's done. It doesn't stop you from doing, anything else. But anyway, one of the things that's very irritating when people say like the Bayesian approach takes so long is that if like journals and whatnot, or, classes that you take on frequentist methods were, required to demonstrate that the point estimator you're proposing to use actually has a normal distribution for the finite n that you actually have that number of observations for all values of the parameters that they could take in the parameter space, that would take a hugely long amount of time as well to establish that with a sequence of Monte Carlo simulations. But you don't actually have to do that in order to publish something in a frequentist journal. You just have to say, oh, this estimator is known to be asymptotically normal, irrespective of what the values of the true values of the parameters are. So I'm allowed to use it irrespective of how small my data set is. And kind of the same thing with supervised learning as well. Yeah, those sorts of things are probably originally motivated to be used in like Facebook size problems, but they get used, in not Facebook size problems. And you might be getting yourself into trouble if you sort of systematically ignore all kinds of uncertainty about the parameters, about the models, etc. So, questions about that? Okay, got that. Another source of uncertainty that people sometimes talk about, I didn't put it among the four because I think it's more or less a solved problem from the Bayesian perspective, is, well, what is the generalizability of my results to other populations? And that reason why I consider that a solved problem basically is you can call posterior predict if you estimate your model with R-stan-arm or BRMS with new data equals something, where that new data frame can be from whatever, or intended to represent whatever population you want to make predictions about. Or, if you do your own STAN program, yeah, posterior predict is not going to work with that. But the idea of posterior prediction, you could do yourself once you have draws from the posterior distribution, and you can, apply those to census data or any data set that is representative of the population you want to make predictions about. And so really the fundamental obstacle is, well, what is the distribution of the predictors in the population you want to make predictions about? If you don't know that, then it's hard, but not because there's any like flaw in Bayesian inference or anything like that. It's just you don't know, what the distribution of the population is going to be in 50 years or something like that. So you have to kind of make some guesses, or you have to put in a distribution of your beliefs for, what the population shares will be in 50 years or something like that. But it's conceptually, it's pretty much a solved problem. But one of the things that you might want to do probably do want to do pretty much always when estimating a Bayesian model, is allow for there to be heterogeneity in the data generating process across, groups. So, if you have a data set, might be a random sample from something, might not. And, let's say it way over represents men, or it way over represents whites, or something like that. Okay. Well, those observations that you have are still perfectly good for updating your beliefs about the parameters that govern the data generating process for white men. Now, if you have fewer observations for other types of people, and you're estimating a multi-level model that has heterogeneity in the parameters, you're going to be more uncertain about groups of people that you have fewer observations on, but you're correctly more uncertain about those things. So even like I said a number of times, the Bayesian inference doesn't hinge on the data you're conditioning on being a random sample from any well-defined population, like frequentist inference ostensibly does. You can use a data set that's not representative of the population you want to make, as long it's still sort of good enough for updating your beliefs about the data generating process for the data that you have. And then there's maybe another step involved in making predictions about a larger population. But anyway, that's easy to do with RSTAT-ARM and BRMS, and it's not too hard to do in the generated quantities block of your own STAN programs, provided you know what population you're trying to generalize to. And you can do stuff like post-stratification, which, weights the posterior predictions you have by the population shares of people in the population you want to refer to. And that works way better most of the time than what most people are doing with design weights from a frequentist perspective, which really only ensure that if the process was done over and over again and you calculated the design weights over and over again and did like weighted means or whatever, that would be a consistent estimator of the population mean. It doesn't mean that the thing is representative in any one particular data set. It's just over the process of taking samples from the population. And so usually working with the data that you have, getting the posterior distribution and going from there is a pretty good approach, particularly because in so many situations in which we have in the social sciences, we don't have a well-defined sample from any, or we don't have a random sample from any well-defined population. We just have like all the data that was readily available. But that's fine from the Bayesian perspective. It's a real problem from a frequentist perspective, even though it's mostly ignored by people who are doing these estimations of models. Questions about that part of it? Okay, so a bit about prior predictive distributions. We talked about that, earlier this afternoon, but also a number of times over the course of the semester. And what I think is interesting, a connection between these and directed acyclic graphs, which have also, in sort of the same time that Bayesian analysis started to take off, directed acyclic graphs started to take off, more so in epidemiology and some fields like that than in social sciences, but are used some in social sciences today, probably should be used a bit more. And they're used to describe or partially describe the relationship among variables with a particular theory. So really all these graphs are a language to communicate what your theory is. And the primary use of them is to tell you, algorithmically, if this is your graph representing your theory, is the causal effect of some variable identifiable by the data under the theory. So assuming the theory to be correct. So if you could get like infinite amount of data, and this is how the data were generated, would you be able to do some calculation that would give you the causal effect of manipulating that treatment variable of interest. And that's all well and good. But they just sort of state the relationship among the variables with arrows and stuff like that. And, conditional on this is these two things conditionally independent and stuff like that. They don't come with distributional assumptions or like how the parameters come into the picture. Because usually making additional assumptions doesn't change the fact that like something is or is not identified under the graph. There's a few situations where if you like assume, stuff is multivariate normal, you can achieve identification, but without that, then it wouldn't be identified. But for the most part, like making an assumption of like linearity or that this is like gamma distributed or whatever isn't going to change the fact that something is or is not identified by a theory, but that's really just identification analysis. Even if something is identified, you're probably going to have to make some stronger assumptions if you want to estimate what that causal effect is from some finite amount of data. And in order to do that, you're going to need to enrich your theory to say, what do you believe about the parameters before you see the data? And what are the distributions we need to plug in for the parts of this theory that involve unknowns? And then how can we update those with data? But I think drawing from the prior predictive distribution sort of fills in the gaps of a directed acyclic graph. It tells the story of how you think the data came to be under your theory, but it adds in some details that are sort of abstracted over if you just look at a directed acyclic graph. And I think that accomplishes a number of purposes. One, it's sort of the only sufficient indication that we have or that you have to demonstrate to yourself that you actually understand all the parts of the model. In my experience and a lot of people's experience, people will say, yeah, like I get it, but they don't actually get it well enough to draw from that prior predictive distribution. And the reason why that is that they didn't actually get it. So, drawing from a normal distribution is not like the hard part. It's putting all the pieces together in order to have a plausible story for how this endogenous known came to be. And so if you can write down the steps of that story using computer code and say, okay, like get the errors and stuff out of it, you can actually get draws, then, you probably do understand it well enough in order to start, doing other things with it. So one of the things you might want to do is evaluate whether your priors on the unknowns and the distributions you used there imply a reasonable distribution for the endogenous known. And this, I think, is one of the main responses to people who say, well, how could you ever know like whether your priors are good or reasonable, or like, someone else could just as easily like say they have this priors and they come to a different conclusion. Well, we can always evaluate even before we see the data on the endogenous unknowns, what is the distribution implied by these priors, and compare that with different things and see whether that accords with what we think the outcome is going to look like marginally. And for people who aren't in the habit of drawing from the prior predictive distribution, like over 90% of the time, they're probably using priors that seem ridiculous when you push it through and evaluate what those priors imply for the distribution of the endogenous known. You'll get things like, the average wage, could be $500,000 or like negative thousands of dollars, or other things that are like impossible or known to not be the case. You'll get like for logit models, people will put in these very diffuse like normal priors and the coefficients and be like, I'm being objective. But those like very diffuse normal priors imply all the success probabilities under the predictive distribution are either 0 or 1. But that can't be the case. Otherwise, like, why are we studying something that we think is going to just like always fail or always succeed? If we're studying it, it has to have like some interior mix of like, some people vote, some people don't. Some people vote for the Democratic Party, some people vote for the Republican Party, and we're trying to understand that. So, you know, it has to be the case, really, for a lot of these things that, you know, the probabilities are sufficiently interior that these things could go either way. But that's not really achieved by a lot of prior distributions, even prior distributions that people thought were a good idea, like not that long ago. Another situation this comes up with like autoregressive models, people whose priors put positive probability that this data generating process is explosive. It's not stationary. And but we don't really observe any variables in the real world that are explosive, at least not in the social sciences. Anyway, so if once you get in the habit of like drawing from the prior predictive distribution, you'll be astonished as to like how unreasonable your priors start off being a lot of the time, but you can like tweak things and adjust it so that you get a reasonable prior predictive distribution. Another connection of this that I don't think people really necessarily got is that the prior predictive distribution, the PDF of that is the denominator of Bayes' rule before you see the data. But the denominator of Bayes' rule is just the integral of the numerator of Bayes' rule that you're representing with a whole bunch of draws rather than doing that integral analytically, because that's usually impossible. So in order to get the denominator or draws from the distribution in the denominator, you got to get the numerator to be like, you know, reasonable and not have crazy priors and stuff like that. And so if you can get a reasonable denominator, then your numerator had to have been, you know, pretty reasonable as well. Also, it got cut off here, but obviously SBC heavily involves the prior predictive distribution because you have to condition on those realizations from the prior predictive in order to get these posterior distributions that you can then look at to see if they're systematically different from the prior distributions in order to judge, you know, whether Stan is going to be working well for not just like in general, but for the particular data generating process that you're trying to model. So those are all important. But we did that a bunch of times, so hopefully people feel pretty comfortable with that. Okay, so I put some review questions from last year's final up on CampusWire, actually several weeks back. So hopefully everybody has seen those. But actually, before we jump into those, are there questions about like big picture things from the semester? These ideas like prior predictive distributions and generative models and the sources of uncertainty and how Bayesian approach inference differs from frequentist approach or supervised learning. Okay. So what are some of these questions? So the first one on there was really just a probability problem. So if U has a standard uniform distribution and Y is equal to U squared, what's the distribution of Y? What's the PDF of Y? Do you have any markers? So how do we do these problems?
We would know that since I guess if we're dealing with something that's standard uniform, then its PDF would just be a solid line, a horizontal line at one.
Mm-hmm.
And since 1 squared is just 1, u squared would also just.
So the first half of that was right. The standard normal density is constant at 1. But we're not squaring the density. We're squaring the random variable u. And so it's actually going to have a density function that is not uniform. And so, for example, like if it can be shown that if you square a standard normal random variable, that is distributed chi-squared with 1 degree of freedom. But if you square the standard normal density, that's not a thing. I mean, it's going to be a positive number. But it's not going to be a probability distribution. It's not going to be a PDF. It's not going to integrate to anything in particular. So for these problems, we're doing transformations to the random variable and trying to figure out what the PDF is. We're like never or almost never applying transformations to a PDF, because that in general is not going to give us another PDF. But we can always work out problems like these. What's the distribution of a transformation of a random variable? So, I mean, these problems have a pretty prescribed steps to doing them. So what's the first like step down that road? So pretty much the one thing we know is that U is distributed standard uniform, or it has some distribution. Here we're asserting it's standard uniform. So what we need is the transformation into U, because we know what the distribution of U is. So how would we transform from Y to U? Square root. All right. So U is equal to the square root of Y, positive square root of Y. Okay, that's step one. So the square root of Y is distributed standard uniform. But we want to know what's the distribution of Y, not the distribution of the square root of Y. Okay. So what's the next step of the procedure that we need to do in order to figure out what is the PDF of Y? We need to take the derivative of this transformation into U. Okay, what's the derivative of U with respect to Y? Okay. So we got that. And then what we do is we take the known distribution, or the PDF that's known, evaluate that in terms of Y, in this case, the variable we want, and we multiply by the absolute value. In this case, it's already positive, so we don't have to worry about the absolute value. But we multiply by the absolute value of the derivative of the transformation into U, written in terms of Y. So as was said at the outset, the PDF of a standard uniform is just 1 everywhere in the parameter space between 0 and 1. So it's just 1 multiplied by this derivative here, half square root of y. And that actually can be thought of as a beta PDF with first shape parameter equal to 1/2 and second shape parameter equal to 1. But those are the steps every time you're doing one of these univariate, what's the distribution of a transformed random variable questions. And you can always make sure your conclusion is right by just doing the definite integral over the whole sample space of what you think is the right answer. If it integrates to 1, you have almost definitely done it correct. And if it integrates to anything other than 1, you've absolutely done it incorrect. So it's the same 2 steps every time, and you have a way to check that is like definitive. So you ought to be able to get these. And these are important because writing good STAN programs often involves working with transformations. And it goes back to the generative modeling thing. Like if you have this 1-to-1 transformation between endogenous unknowns and endogenous knowns, you can flip things around in your STAN program and just, transform it one way or transform it the other, as long as like what the transformations is, and it's a 1-to-1 relationship. And so like if you were doing this in a STAN program, sometimes it would be easiest for STAN for you to declare u in the parameters block, and then y is the square of u in the transform parameters block, and then go from there. But you could obtain the same implications if you put y in the parameters block and u is the square root of y in transform parameters. So conceptually, the u, like whatever follows from that, is going to have the same implications. Like whatever your utility function over all of this is going to be the same no matter whether you make u the parameter and y the transform parameter, or you make y the parameter and u the transform parameter. So you might say, okay, it doesn't make any difference. Well, it makes a difference to STAN because the posterior distribution with respect to u is a different thing than the posterior distribution with respect to y. Even though they have all the same substantive implications to u, the shape of that posterior distribution that STAN is like drawing from by going through the parameter space with Hamiltonian Monte Carlo, it's different if the underlying thing is this beta PDF than if the underlying thing is the standard uniform. And really anytime you declare a restricted parameter space in your parameters block, STAN behind the scenes is already doing these transformations from the real numbers to the constrained parameter space that you do. And so when you're doing this posterior distribution of u or whatever, there's actually a transformation from the real numbers to the 0-1 interval. It's actually doing a logit transformation in order to make that happen. So a lot of the stuff that's going on with STAN is just like transforming from one step or one space to some other space, and trying to find the transformation that makes it easiest for STAN to draw from this posterior distribution with a high effective sample size. But when you have like all these transformations, it gives you flexibility to try things different ways in order to achieve that good effective sample size while still keeping all the implications substantively of your model, they're unchanged. So that's why one of the reasons why we sort of did several of these problems where we worked through transformations. And one of the most important ones is the transformation from standard normal to general normal. You know, multiply by a standard deviation, shift over by an expectation. You can go from standard normal to general normal. But standard normal is by far Stan's favorite distribution to draw from. So anything that you can do transformation wise to make your posterior distribution be closer to just like independent standard normals in k dimensions is going to be a good thing. And that principle is really behind, like in our Stan arm, Stan LM and Stan GLM or whatever has this option for QR equal true. Well, we're not going to go through the matrix algebra today, but that's basically just a transformation that tries to make the posterior, it's a bijective transformation with some matrix algebra that tries to make the posterior distribution closer to independent standard normals. And then, okay, we draw from that posterior distribution, and then we reverse the transformation in order to get a posterior distribution that's implied by our model for the betas, the coefficients on our original predictors. And doing that tends to get faster convergence, fewer function evaluations, better effective sample size, etc. But a lot of what's going on with Stan is really just transformations of random variables. And so these like fairly simple things are, you know, ones you need to learn how to do. Questions? Number 2. This was a problem about fish, or about how many fish get caught. So there's a data set, it's pretty common. Has like 250 observations on 5 variables that were collected from people who go to some like national park or whatever. And one of the things we might want to do a hierarchical model of is how many fish do they catch? So we could easily specify a hierarchical model like this, allowing the coefficients to vary by persons, which in this case is an integer, but we can include it as a grouping factor for like the number of people that were in the group doing the fishing. And so this is something fairly easy to specify in our Stan arm or BRMS, this hierarchical Poisson. You can choose priors. Remember, by default, the priors on coefficients in BRMS are improper uniforms, which is probably not the best choice, but one that you can easily choose yourself to be something more reasonable. In some cases, you need to increase up the adapt delta to get rid of some of the warnings. That can be done as well. So one of the things we talked about it, I think, last year, but didn't really talk about it this year, is these zero inflated Poisson processes. So the Poisson distribution is not really that appropriate empirically for a lot of things in the social sciences because it only has one parameter, and that sort of implies a lot of magical properties, inclusive of the expectation is equal numerically to the variance. But that isn't an assumption that is satisfied a lot with social science applications. So one of the reasons why it might not be satisfied is that there's over dispersion in the count process. The variance of the conditional mean is smaller than the conditional variance empirically. So that can maybe be addressed with like a negative binomial, which adds a parameter, and it's sort of a limiting case of the Poisson distribution and can be used to take into account over dispersion. But another reason where the Poisson distribution often fails in social sciences, we have a lot of count processes that turn out to have more zeros than what is implied by a Poisson model with like whatever mean. Like 0 is a valid value for a count, but if like the expectation of a Poisson is like 10 or something, 10-ish, then the probability of observing a 0 is pretty small. But a lot of these count processes we observe, we see like too many zeros to fit into Poisson. And so one of the things that you can do about that is estimate what's known as zero inflated Poisson or a hurdle model. Those are actually slightly different things, but the basic idea of it is, well, first there's this Bernoulli random variable that indicates whether the count is like 0 or positive. And then conditional on the Bernoulli random variable being 1, indicating there's a positive count, then conditional on the thing being positive, then it's Poisson or something like that. Different models make different assumptions. So there's sort of, in this case, 2 mechanisms by which you could end up with 0 fish. One is you go camping, but you don't fish. Or you could go camping, you could fish, but not catch any fish. And so in the 250 observations, the zeros are going to come from both ways. So you might want, it doesn't, we don't have a variable in here that says like, did you attempt to catch any fish? But the variable we do have, how many fish did you catch? It has a lot of zeros in it. And so we can model that as, okay, there's some probability you did not attempt to catch any fish, in which case you probably didn't, unless the fish just like jumped out of the lake into your tent. Or like you tried to fish, but you just didn't catch any fish. So we can do a mixture of those 2 things. And that is also relatively easy to estimate with BRMS, although not R-stan-arm. If you do like 0 inflated Poisson as your family. So you could look at the documentation on that. But, you know, you can think of lots of situations in which, you know, having like a lot of children in the camping site would make you like more likely to fish, but less likely to actually catch any fish because children are terrible at fishing. Sort of thing. But you got to think through the data generating process in order to come up with a reasonable model for something like this. Anyway, if you just did this, you would find, and you do the posterior predict, like all that posterior predict and base plot, that all works reasonably well with BRMS. You'll get posterior predictions, but the posterior predictions are all like tending to predict like 1 fish or 2 fish or whatever, but the actual thing is 0. So you see a discrepancy between what the model predicts and what actually happens. And, you know, you might have some ways to go from there with like 0 inflated Poisson, 0 inflated negative binomial, hurdle models, these sorts of things. So questions about doing hierarchical models with BRMS? Like I said, the R-stan-arm BRMS are intended to make these sorts of things relatively easy, at least to specify, but you still have to think through the generative model, what would be reasonable priors, like these sorts of things. Just sort of jumping right to it is often not going to give you a good result. So the third question was about the 2018 Kentucky Derby. Lots of good questions could be asked, you know, for something like that. I put a post about it on Campus Wire, and then like this year it went totally crazy because the horse that finished first got disqualified, and does sort of underscore the fact that for a lot of like data that we ostensibly observe and measure in social science, there's controversy over what the values are. Like under the rules, like there's sort of an official winner but like, did that horse really run the fastest of all the horses? Well, no, but anyway. So in 2018, things made a bit more sense. There's a horse, Justify, who actually won the Kentucky Derby and the next two horse races. But anyway, like in the afternoon of the Kentucky Derby, the odds that Justify would win were 5-2. So if you bet $2 on Justify to win, that would have an expected value of 0 if the probability that he wins is 2/7, which you could obtain just by plugging in, how much money would I get if he wins? How much money would I lose if he doesn't win? What is the probability of winning that makes my expectation be 0? And that would be 2/7 in this case. And then we'll skip that second part for a second. So after he won the Kentucky Derby, then there's another horse race called the Preakness that happens 2 weeks after the Kentucky Derby. And the starting odds for Justify to win the Preakness were now 3-2. So if we suppose that the sort of betting market's prior beliefs are governed by a beta distribution, what shape parameters for that beta prior before the Kentucky Derby happened would be consistent with the updating we see as a result of this horse winning the Kentucky Derby. Anyway, so we know if we have a beta prior and a Bernoulli likelihood, like we learned with the Ebola thing, well, that had a binomial, but Bernoulli is just special case of binomial with one try. We knew that the beta prior is conjugate with the binomial likelihood, and as a result, the posterior distribution can be written in an analytical form in this case, where sort of the updated parameters for that beta distribution, once you condition on the data, you put the number of successes, you add that on to the first shape parameter, and the number of failures, you add on to the second shape parameter. So in this case, we have one success, Justify the horse won the Kentucky Derby, and no failures. So the second shape parameter stays the same. The first shape parameters goes from whatever it was to one more. Also, we know under a beta distribution that the expectation is equal to first shape parameter divided by sum of the shape parameters, A plus B. So we know, like before the Kentucky Derby, the expectation was 2/7. That, or at least that was what the market was saying for the probability that he went. And then after the Kentucky Derby, the probability of him winning the Preakness implied by the market was 2/5, which is equal to A star over A star plus B star, and A star is equal to A plus 1. So now we have two equations, two unknowns, A and B, but we know two values of the expectations. Started off before the Kentucky Derby 2/7, and then after the Kentucky Derby before the Preakness, it had gone to 2/5. So solving two equations and two unknowns, not really a big deal. We find that the shape parameters that are consistent with this updating is A is equal to 3/2 and B is equal to 15/4. So if that's what like the market had as its prior before the Kentucky Derby, that would make sense if it used Bayesian updating to then get the odds for Justify to win the Preakness 2 weeks later, conditioned on the fact that he won the Kentucky Derby. And he actually did win the Preakness and the Belmont. Okay. So this is basically like, can you apply Bayes' rule when we have an analytical solution? And can you work with the properties of the beta distribution, which is an important prior for doing Bayesian analysis for these things that are constrained to be between 0 and 1, or really any two known lower and upper bounds, because you can always like rescale that to the 0, 1 interval. But in terms of actually doing this, like even if you didn't know that the beta distribution was conjugate with the Bernoulli likelihood, you could just write this as a Stan program or do it in RStanArm. And you're going to get back draws of all this. So Stan does not rely on the prior being conjugate with the likelihood. It doesn't particularly care. And so if a conjugate prior is the easiest thing for you to express your beliefs with, like, you know, maybe with the monkeys and stuff like that, then go ahead and use a conjugate prior. But it has no bearing on how Stan is going to draw from this posterior distribution. And so if a conjugate prior makes it hard for you to specify what your beliefs about the parameters are before you condition on the data, then don't use a conjugate prior. And one of the ways in which this comes up is the conjugate prior under a multivariate normal distribution. The conjugate prior on the covariance matrix is this thing called inverse Wishart, which no one understands at all. But it was used, and it was used routinely for like 15, 20 years there, because it was like the only prior you could use on a covariance matrix in the bug software, which had to rely on conjugate relationships in order to draw from the posterior distribution with a Gibbs sampler that, you know, relied on the full conditional distribution of like one thing conditional on everything else. So even though nobody understood what the inverse prior implied, we knew we could, you know, draw from its full conditional distribution, conditional on like everything else, and get draws from the posterior distribution. But, you know, people had no idea what to use for the hyperparameters on something like that, because it was not only not intuitive, but inverse Wishart prior is just really weird. And so what Stan has been able to popularize is a different approach where you separate covariance matrices into like a correlation matrix and a set of standard deviations that multiply that covariance correlation matrix to turn them into covariances. And so correlation matrices are easier to deal with than covariance matrices because it's a convex set, and we can put a LKJ prior that's uniform over that convex set on the correlation matrix, which a lot of people are like way happy to do, because otherwise it's sort of hard to think about a good prior for a covariance matrix. Like either uniform or slightly peaked on the identity matrix are basically the only two choices that anybody ever really uses or thinks are reasonable. But if we separate it, okay, we have a good way to handle a prior on a correlation matrix, and we have like a variety of decent ways to handle priors on standard deviations. And so if we've got the correlation matrix, we got our standard deviations together, those imply as an endogenous unknown a covariance matrix. But we didn't have to put priors directly on that covariance matrix. We just had to put priors on the correlation matrix and the standard deviations. And then it was just like multiplication in order to get a realization of that covariance matrix. And so factoring, separating complicated random variables into simpler parts has been an important part of doing things well in Stan. And we're able to do that because we're not restricted to conjugate priors. We can just focus on what priors make it easiest to specify your beliefs. Okay, so there was another part of this question that actually pertained to some social science. Like in what, for a lot of these things these days, there's some like website in some like poorly regulated country that allows you to place bets on like all kinds of things these days, like who's going to win an election, or like obviously gambling, but you know, all sorts of other things, like what are they going to name the baby that Prince Harry just had, or like you can bet on pretty much everything these days. But those, in a manner of speaking, sort of give you a dollar weighted expectation of things that are not known in the present but will be known unambiguously in the future. So in what sense are those Bayesian? In what sense do those help us choose priors? In what sense do they not really help us choose priors?
I think we can just use the distribution of whatever exists in the market and then make a model of prior distribution.
Yeah, I think it's not quite that simple because the market, so you have this sort of equilibrium maybe that you could say is the expectation, but you don't really see the whole distribution because there's all sorts of trades that don't happen in equilibrium. So yeah, like when the Kentucky Derby, you can say, okay, the market, it's implying he has like a 2/7 chance to win. Nothing explicitly said that has to follow a beta. Like that's the expectation of a beta distribution. It's just the expectation of some random variable that's defined on the 0-1 space. So it's an additional assumption to assume that's beta. And if you do assume that's beta, well, the beta has two shape parameters. So the expectation sort of pins down one of them, but the other of them is free. You need an additional source of information or something to like complete a beta prior. Now, if we observe two horse races and we know like he won the first one, okay, now we have like two equations, two unknowns. Still, nothing says like this has to be a beta prior, but if it was, we could solve for both things. So they do give us prior expectations in a manner of speaking. They're not necessarily your prior expectation. It's sort of the prior expectation of other people, but it's also not like equally weighting other people. It's weighting by how many dollars are bet on like one side of the futures market or the other. So it's sort of dollar weighted prior expectation. But that could still be a pretty reasonable starting point for these sorts of things. They're also definitely subjective probabilities. There's no sense in which like the 2/7 or whatever that the market arrived at before the race happened was a result of some frequentist thing where they secretly ran the Kentucky Derby like a million times and 2/7 of the time justify one. Like that did not happen. Not going to happen. And in a lot of situations, this idea of repeated sampling or repeated something that induces a distribution that we can take the limit of to figure out the probability, it's just a thought experiment in the first place. We may not have like even one random sample from that process to begin with, but in a lot of situations, we still need to figure out a probability in order to decide like how to bet. Or how to invest, or whether to open a factory, or all these sorts of things depend on future unknowns. But we have to sort of take some position on what those future unknowns are in order to move forward. But as we move forward, we can update our beliefs about the unknowns as we get new information, such that, you know, Justify the Horse actually won the Kentucky Derby and won it pretty easily, that we can condition on as we move forward. Questions about that? Okay, got that. So fourth question was about a couple of questions about this picture here. So what do we have going on here? We have like maybe this is not any actual data. This is just sort of stylized representation. We might have a posterior distribution that looks like this, or even a prior distribution that looks like that, for the effect of some treatment. And then the first question is, the first plot says the probability the causal effect is positive is equal to 0.987. So what calculation would have resulted in 0.987? Yes. So the area under the curve to the right of 0, the area under the whole curve is 1. So the area to the left of 0 is 1.13, 0.0113, whatever. Or in practice, like we would probably gotten a whole bunch of draws from this posterior distribution. So what operation on those draws would have given us something like 0.987? What's the simulation equivalent of doing a definite integral?
Do you mean like 1,000 draws?
Yeah, or
And then
10,000
you
or
get
whatever.
987
Yeah.
positive.
Right. So what proportion of the posterior draws are positive? So could get at that either way. Then the next question was about, okay, based on the information provided in the plot, should you or should you not implement the policy that ostensibly has this treatment effect? So what plot do we need to look at in order to make that determination?
Get the area under the third.
Under which curve?
The third one.
The third one. So posterior density multiplied by the loss function. So here's a somewhat reasonable but stylized loss function in the second thing. So there's some fixed cost to doing this thing that gives you a loss of 20 whatever units. And then, okay, after you do the fixed cost, there's some positive treatment effect, but maybe it's diminishing, according to what you estimated here. Okay, but that's just your loss function. What we need to do is weight the loss function by the posterior density of all the things that can happen and integrate over it. So here we have the product of those two things, the posterior density and the loss function. And so this is getting the expected loss and seeing whether that is negative or positive. So in order to get the expected loss, we need to do what it says on the plot, need to integrate this function over all real numbers. And if you look at it, it may be a little bit hard to tell on this screen, but if you look at it closely, it's pretty clear that the amount of negative area is greater than the amount of positive area here is greater than the amount of negative area over there. And since this is in terms of a loss function, positive loss is bad and negative loss is good. So we have more positive weight put on the over here than negative over there. So that would conclude we should not do this, even though we're almost positive that it's going to have a positive effect. But that doesn't say anything about the costs. So we also have to have a substantive function that we weight by a probability function in order to figure out what would be the thing that maximizes, what would be the decision to do this or not do this that would maximize our utility. Okay. For those of you who can stay, there's just like one more problem about beta regression. So we talked about our stand arm, and it can do a bunch of different things. I don't think we talked about this model in particular, but what if you have a outcome variable that's a proportion restricted to be between 0 and 1? Well, you could model that with like a beta likelihood whose expectation is a function of predictors. And then there's another parameter to the beta distribution. So you can parameterize it with mean and variance, or like mean and this concentration parameter thing. Talked about in the Krushke books, different ways of parameterizing the beta distribution that all have the same expectation. And so usually when doing like generalized linear models, even if we're doing them in a Bayesian sense, always if we're doing it in the frequented sense, but most of the time when we're doing it in the Bayesian, what we want to do is parameterize the distribution so that one of the parameters is the conditional mean. And then we'll set that equal to some like inverse link function applied to the linear predictor. And then if there's any other parameters to the distribution, we'll just sort of tack those on and get the posterior distribution of those. So we can easily do like stan underscore beta reg to model like, you know, proportion of people or a proportion of how much people spend on food of their income, you know, as a function of like how much income they have, how many people they have in the household, any other predictors like that. And we can specify priors on all sorts of things and get posterior distribution of the intercept and coefficients and, you know, anything else. And then we can do posterior predict and all sorts of other stuff to see, you know, is this actually a good model? And in this case, it probably wasn't, but that was sort of one of the things that the question asked you to find. So I would, you know, we didn't do like every single piece of the review problems. Also, like, you know, there's going to be stuff where you're going to have to write your own stan syntax. Like, how would you do this sort of thing if you were going to write your own stan program to do it? So, but those are the things that we covered in the last couple of weeks. So hopefully you understand a bit how to do that by now. I didn't think we needed as much like review on how to do SBC and stuff like that because we like just had a homework about it. But some of these other things that we did farther back in the semester, I thought it would be worth revisiting. So I would take those things off Campus Wire and, you know, make sure you can do some of the stuff that we didn't explicitly talk about, like look through the posterior predictive distribution and, you know, could you calculate Lu and, you know, those sorts of things like that, that other parts of the questions asked about, but are probably reasonably straightforward once you can get like the initial steps for like how to set up the model or what the priors are, like that. Questions?
Only way Stan can if it's run out of error.
You can use anything on the internet. So the old homeworks or whatever it may be. I'm not going to be able to say like, oh, you should change it like this. Some people I think didn't appreciate that if you have errors or whatever and you go in RStudio and you click check, it will give you like more information about the errors. So RStudio has done like a really cool thing by like as you're typing, if you make an error, it has like a little X in the left margin and you can like hover over that. And that might give you enough information to see what the error was, but it might not. So if you click on the check button, it will then like give you a more expansive set of information. But that's mostly just for syntax errors. Presumably, we've had enough practice that you can like, if you're missing a semicolon or whatever, you can figure out where to put that in. And so the bigger question is not so much like, does this have the right syntax, but is this like, one, does this thing that I wrote down actually correspond to the model that I wanted to estimate in my mind? And if so, like, or if not, like, why not? But then there's like more questions like, is the model that you wanted to estimate in your mind a good one? But those are the sorts of things that I'm not really going to be able to like help you with during the exam. But hopefully we've talked about enough things to where you can figure some of those out yourself, at least retrospectively, with like posterior predictive checks, or prospectively with SBC. Now, we're not going to do like a SBC problem on the exam because it just like takes too much computation time to do it. But we might have problems that like it would take a lot of time if you were to actually like draw from the posterior distribution. But the problem will be like, how would you write a STAN program that does this? Not necessarily like, how would you write a STAN program that does this and then like download a data set with 1 million observations and like sit there for half an hour while it, but so we're not going to spend a lot of time sitting like waiting for stuff to compute. I mean, it'll maybe take 30 seconds to compile, but if we're actually like drawing from a posterior distribution, it'll be with a small data set. And so you need to think about the sorts of things about like priors being more important with small data sets than larger data sets. And like, there's limitations as to how ambitious you can be with estimating, crazy hierarchical models and stuff like that if you don't have a whole lot of data to begin with. But anyway, we're not going to just sit around for a long time during the exam.
I have a question. It seems like the sample you gave us, the questions from the sample you gave us does not ask us to write the STAN program.
Yeah, so one of the questions actually on the final exam was like, write the posterior density for that constant elasticity substitution thing that we did a homework problem on. So that was like another piece of the exam. Yeah, so you are going to have to write like some stuff in the STAN language, like draw from a prior predictive distribution and things like that. But you definitely need to be able to do things in BRMS and RSTAN ARM, not just like estimate the thing, but sort of the whole process of comparing it with other models and things like that. And so hopefully those sorts of problems you can get through pretty quickly.
So how many questions do we have?
4 or 5. I mean, they have sub questions within them, but it's a 3-hour exam.
Yeah, no, the data mining one's really.
I think we had maybe more than 5 questions on the data mining exam.
7.
Yeah. Yeah. So this will probably be like fewer questions than that, but more thinking involved. So data mining class did not encourage thinking. It encouraged doing. So you have to do stuff with Bayesian analysis as well, but you still have to think.
Do we have more examples of that?
I can maybe come up with some more stuff, but it seemed like people were still working through the ones that we had. There's no shortage of questions. I mean, we could do it. I mean, Columbia won't let us, and it's probably not worthwhile, but we could easily have like a 10-hour exam over the amount of stuff that we've covered. But yeah, it's no particularly big deal to make like 2 practice 3-hour exams and 1 real 3-hour exam. But yeah, I mean, one of the, I think, good exercises to go through is just like write an exam for yourself or write it for each other. Like you ought to have a pretty good sense of what the questions are going to be, because what the questions are going to be, you know, the important parts of doing a Bayesian analysis. So just the process of like thinking through like what those questions would be and like asking each other. Like, I think that's probably a pretty good way to study over the next week. Okay, so I'll have office hours on Thursday afternoon. You can always post things on CampusWire. I think gotten away from doing that as the semester had gotten closer to the end, which is unfortunate because like there's a lot of good things to discuss more, particularly if you have questions about them. But the NYU students have been asking a lot of questions, even though they're like the quarter started in April for them. So we're just sort of now getting to like how to do stuff in Stan. But if you've been following along, you see they asked a lot of the same questions that you all had in like March or February about like priors and stuff like that. So looking through those is probably a good way to review as well, and certainly chiming in if you have additional questions or additional aspects to the answer, follow-ups, stuff like that. Okay, well, I will see everybody around, and particularly on Tuesday afternoon, if not before. All right, so where are we?